Hey, Lindy, how's it going?
I'm
What's up,
good. How are you?
Jonah? Good, thanks. What's up, Jonah? Hey, Joseph. What's up, Adrian? How you guys doing? Y'all ready for a test on Thursday? Hey, Eiley. Eiley, I didn't get a quiz from you on. Oh, Lindy, I don't think I got a quiz from you either.
Okay,
Fro-
I'll make sure to turn it in then. I
From
must have just
oh
forgotten.
no, Lindy, I think I got yours. I think it was just Eiley. Eiley, double check. I think it was there wasn't an upload. Um. All right, I got 310. Let's get started. Test on Thursday. So today we'll just review. These are your topics. Now I'm going to share this. Sorry, 1 second. I'm going to turn off your faces. I'm going to share this video. Actually, yeah, that'll work. You share this video with my online class because their test is coming up, and it's going to be basically on the same stuff, almost the same stuff. That's why I have 2.5 up here. That's not on your test. 2.5 is not on your test. Implicit differentiation, you were tested on that last time. That'll be on their test. So you guys are 2.6 through 4.1 related rates. Last topic we covered in chapter 2. And then 3.1 kind of stands alone, right? In that 3.1 was that absolute max min on a closed interval. So you, at most, you get one question from that, because from there, then we kind of handled out, we figured out how to handle open intervals, right? Or like the entire domain of the function. So 3.1 is not a terribly important section, but I might ask you one question. Okay, 3.2 to 3.6, I just kind of put those together as like one topic. But that, of course, is first what the first derivative tells you, increasing, decreasing max min. And what the second derivative tells you, of course, concave up. We've done a bunch of these by now, right? Concave down, and inflection points. Okay, you will not be allowed to use a graphing calculator. You will be allowed to use a scientific calculator if you want. You probably won't really need, well, maybe for some of those word problems, optimization, like on your quiz, I think you needed a calculator to get that cost output. We can go through that one if you guys want as review. Related rates, you might need a calculator. A lot of times we're leaving our answers in exact forms anyway. Okay, so where do we want to start? I guess, were there any homework questions from 4.1? I guess we could start there if you had any. Basic.
I had a question. Mine was question 19. It was the word problem one, second to
Okay.
last.
Can you read it to me?
Let me open it up real quick.
Yeah. I can try and find it as well.
Okay, I think I got it.
Okay.
Okay, it
Go ahead.
says assume the acceleration of the object is a of t is equal to negative 32 feet per second squared. It says neglect air resistance, and it says a balloon is rising vertically with a velocity of 16 feet per second, and it releases a sandbag at the instant that the balloon reaches a distance of 80 feet off the ground. And the first part is how many seconds after it is released will the bag strike the ground. So that's the
Okay. Let's see. This guy only you had different values for 5 and the 50.
It's not 20, it's 19.
Oh, 19.
Mm-hmm.
Okay, good. Yeah, let's do it. Okay. All right. So Joseph, what was your plan of attack here? What did you do first?
Well, I kind of did a different approach. I kind of used kinematics instead of doing what
Okay.
we were normally doing.
Okay. Yeah. If you've had some exposure to that, that might work. Let's try and approach it from our. I think this is going to be like a position function, velocity function, acceleration function, right? Because they are giving us the acceleration due to gravity. Now, we haven't done this. We didn't do this in class. We went the other way, right? I gave you a position function. You took the derivative, got velocity, derivative, you got acceleration. But if we go the other direction, we now know that I can take the antiderivative of the acceleration function, and we call that the velocity function. And that would look something like that, right? And then there might be some given information to find the velocity at time t at a particular moment in time. And then we could take the, let's call this C1. And if we did the antiderivative of the velocity function, we would get something like that, right? And that should look familiar to us, only we gave this guy a special name, initial velocity. We gave this guy a special name, initial position, and 32 divided by 2, of course, is 16. So that's our approach, I think. But let's go ahead. That's a little background how we can go the other direction. We've gone in the past from position to acceleration by differentiating. Okay, let's take a look. Balloon rises vertically with a velocity of 16 feet per second, releases a sandbag at the instant when the balloon is 64 feet above the ground. Okay. This tells me that that's constant velocity. How many seconds after it releases will the bag strike the ground? So we got a couple approaches here. I think we could attempt to find the position function. That's one way we could do it, or we could just try and work with the velocity function. But let's see. First of all, Joseph, does it make sense that how I got this function, the velocity function?
Yeah.
Okay. And then if I anti-differentiate that, I get that. So I guess what we want to do here is see if we can't find C1 or what we would call the initial velocity, right? So it sounds like a balloon rising vertically with velocity. It sounds like that's going to be 16. It sounds like the velocity. A balloon rising vertically with a velocity of 16 feet per second releases a sandbag at an instant when the balloon is 64 feet above the ground. How many seconds after release before it strikes the ground? Yeah, at what velocity will it strike the ground? So I guess one approach would be to try and find this position function. And then the other approach would be, well, I think that'll work. I think we can find this. Any suggestions, or you guys that got this one, how did you solve it? Anybody? Anybody
I
get
think
this
I
one?
tried to find the position.
Yeah. Did it work?
Yeah.
Okay. So, Lindy, what did you get for your first value for C?
Let me see. I'm finding it. I got 16.
16 sounds right. It sounds like it's just going up at 16 feet per second. I don't think, I'm trying to think what other options. It's a little confusing, I think. I don't know if it's 100% clear, but if you read it, there's not a lot of options for your first velocity here. I guess you could solve, this is it's like a hidden initial condition problem, right? So you could say, what was the initial velocity? Well, it started when the time was 0 at it was 16, right? That's how it's been given to you in the past, right? Or for these initial conditions without the application. So you could kind of treat it that way, and then it would go something like this: negative 32 times 0 plus this C1, and then that'll give you a 16 here. So I think that seems right without too many other options for the initial velocity, right? It just tells you the velocity, but we're going to interpret that as initial velocity. And then when we anti-differentiate again, all right, now that we have a value for this, then we take for the position function, we take the antiderivative of this guy, and that gives us our negative 16 t squared plus 16t, plus S naught or C2 or whatever you want to call it. Okay, Lindy, so what did you do for your initial position then?
I did, in this case, I think it would be 64.
Would be 64. So you got to remember, like, what I think what's confusing about this one is that, right, this is when your model is like starting, right, and then it's going up. So you want to say your initial position is 0, as you're tempted to say, but the way we're interpreting that is we're trying to figure out what happens when you drop the item, right? So we need a position function. If we're going to answer the question, we need a position function that starts here, and time represents where we are in this as the thing falls, right? Which I think is a little confusing. But with our interpretation of acceleration due to gravity without air resistance, this is what's happening, right? It's just vertical motion. So our initial position, again, you could treat the 64 like when time is 0, we're at 64. So we're building our model, but it starts for the question how long it takes to hit the ground when you drop it, right? So that'll give you a 64 here. Joseph, what do you think? Does that make sense how we built that one kind of backwards?
Yeah, I understand that part. I was just confused on the velocity part.
Okay. Oh, how we got to 16?
No, I understand that now, but when I was reading it,
Oh, yeah.
like I was trying to I was looking at the equation that I had, and
Yeah.
I just didn't know if I was like setting it equal to 16 or like.
Okay, yeah, that's going to help us get. And once you get the part that our model really starts like up here when you drop the bag, the initial velocity is how fast is your bag going, or whatever they dropped. It's going 16 feet per second up, right? Yeah, so it's the initial velocity. So I guess the better way to think about it is your model starts here, right? So what's the velocity of the object when you're here? Well, it's going 16 feet per second in the positive direction, right? So that could give you that. And then what's the height? Like Lindy said, you're 64 feet above the ground. Yeah, so what I think is confusing is that you're tempted to say, well, the initial position's here, right? Because this is when the thing's starting from the ground, right? But you have to kind of jump to the fact that when we answer this question, your initial position will be 64, initial velocity 16. And you don't even have to remember, you've been given this function in like an algebra class, right? You've probably seen this before calculus. So I don't even have to, this anti-differentiation, I don't even have to do, right? I did this to get that, and I did this to get that. But all this anti-differentiation just gives me the formula you've had for a while. So you could just drop your 16 here and drop your 64 here. Okay, that's a tricky one. But yeah, can I skip the rest? Does it make sense now? Just now the rest we've done before, right? You set this to 0 and solve. We did that in the derivative portion, and then you can figure out the velocity when it hits the ground. Good question. Other questions on the homework? We didn't do these in class. Did you figure these out? I gave you the second derivative, and then you have information. That's actually like the one we just did, because acceleration is a second derivative. See these on your, not too bad, right? If you can do the derivatives, you should be, if you're confident with your derivatives, you should be fairly confident with your integration. No questions? Okay, good. Let's review. Sorry, I'm working with one screen today. And it's a little bit tricky. Okay, here is your review. So I found a couple decent. I think we definitely want to do this question. We could always practice with our word problems. You guys seem to be okay with your oh, you got review questions, Lindy? Good. Yeah, we can do some of those. I forgot. I had that test review from WebAssign. Let me pull it up real quick. And Lindy, you can point out which one, Lindy. Let's start with which one you want to start with.
I guess probably question 7.
7.
Go in order.
Okay, good. Okay, good. So again, so be ready for the curve sketch. I'll probably give you one where I make you do everything. So you gotta be real careful on your derivatives, right? If you remember that quiz I gave you, it wasn't the last quiz, the one before, I guess, where I gave you the second derivative and I gave you the first and the second, so I could see that you're doing the stuff right, the interval, the first derivative test and the second derivative for concavity. But I think I'd like to give you one question where you have to do everything, right? So you got to be real careful with your derivatives because, of course, if you get the first derivative wrong, then everything's wrong. If you get the second derivative wrong, then half of it's wrong, right? So expect probably one of those. I know they're long questions, but one where you do everything, okay? And then expect questions like this where I just kind of break down chapter 3 into different parts like this one, just the first derivative test part. Okay, good. So we want to take the derivative of sine plus cosine on just 0 to pi. So Lindy, what did you get for the derivative of sine plus cosine?
Cosine minus sine.
So my function is sine plus cosine. The derivative is cosine minus sine. And then Lindy, you're going to take that to 0 and solve. Oh, this is a little bit tricky. Is that where you got stuck with that thing?
Yeah.
Yes, this is a little tricky. If you want to remember, when you solve trig equations, we always want a single trigonometric expression. So we'd have to do a little bit of algebra manipulation and maybe a simple trig identity to find this. This one comes up every once in a while. Or I guess you could kind of, if you know your trig pretty well, you could just say, okay, where is this true? Where does cosine equal sine on 0 to pi? Lindy, you probably know that, but it's just a weird equation, right? Because it's when we want to solve equations, we want equations to be one trig function, which I could do. Yeah, I get a little creative with this one. If you divide by cosine both sides, provided that cosine's not 0, then you end up solving this equation. Right, cosine over cosine, and then sine over cosine. I think that should work. Yeah, so I guess you could. That's just kind of not a very common trig equation. When does sine equal cosine? Well, you should kind of say, well, that happens in quadrant 1 at pi over 4, and in quadrant 3 at pi over 4, right? I guess that'd be 5 pi over 4, right? Because the sine of pi over 4 is root 2 over 2. The cosine of pi over 4 is root 2 over 2. And it happens again in quadrant 3. The sine of 3 pi over 4 is negative root 2 over 2. 5 pi over 4. And the cosine of 5 pi over 4 is also negative root 2 over 2. They're the same. Or you can change it to a tangent function and you get the same results. So we get pi over 4 and we get 5 pi over 4. And then we test between the two. So Lindy, does that make sense? Can I skip the testing part? Because I think you got hung up on the.
Yeah, I was just confused with like setting it to 0.
Okay, does that make sense now?
Yes, thank you.
Good. Sorry, I'm not used to using one screen, and my stupid WebEx drop down just keeps popping up, and then I lose my picture of you guys. Okay. So if you're shaking your head yes or no, sometimes I might not be able to see it today. Also, if I'm on a public Wi-Fi, so if for some reason we drop, just hang out and I'll be back. Okay, good. That was a good one. So I stopped it there, but remember, if we were to keep going, we have to do the first derivative test, right? Like we always do. I'm just going to skip that part. We'll probably do this a couple times today. Okay, good. Lindy, what else we got?
Just 17.
17. Okay. Yeah, I know these are kind of annoying when you have to like type in one by one. Maybe it's not too bad. All right, let's do it. So I got to take the analyze sketch the graph of the function. That's a weird looking graph. It looks like a polynomial, but then I got this rational piece. So we could make a note that the domain is all real numbers, but x equals 0. And there's a good chance that x equals 0 is going to come with us for a critical number and what I call possible inflection point, for lack of a better term. But let's take a look. Insert blank page. All right. Derivative. So f prime of x equals, let's see. Let's get you guys talking. Eiley, give me the derivative of this function.
Would it be 3x squared plus 1 plus or minus 4x then negative 2?
Very good. And let's see, Lindy, I'm guessing that is this what gave you trouble, this weird looking function that you have to solve?
Yeah, I think so.
Okay. So what you do with this one is, so this has a fraction. So the algebra here, my initial reaction is to get rid of the fraction, right? So if I multiply the LCD, which is x squared, I'm going to get this thing, 3x to the fourth plus x squared minus 4 equals 0. And again, what we have to watch out when we do stuff like that is that we've lost the fact that x cannot be 0, right? We lost that when we ran that through. That's an old algebra thing that you got to worry about. So if I solve this equation and get x equals 0, I got to watch out. That's called an extraneous solution. However, we don't really have to worry about that because I think we already know. Maybe we should make a note that x can't be 0 anyway. Okay, and that's going to be, actually, I take that back. I know what we lost. We lost the fact that that's a critical number, right? When I did that algebra step, so that's when we should take a note of this. Don't forget, critical number x equals 0, right? Because your derivative is undefined when x equals 0. And then when I set to 0 to find those other critical numbers when the derivative equals 0, then we can solve this equation to get that. I guess the safer thing to do, here's the safer thing mathematically. I would do this and just remember that a critical number is x equals 0. The safer bet is to just make this one fraction, right? Because then we'll have a true rational expression equal to 0 with a denominator that we can consider, right? So that would be LCD. It's a lot of algebra stuff, right? So this would give me the same thing I have over here, 3x to the fourth plus x squared minus 4 all over x squared. And now this looks a lot better, right? Because now I can say, oh, critical numbers, set the denominator to 0, set the numerator to 0. Okay, so either one of those algebraically works. This way works as long as you take note about the x equals 0. And the better way to do that is really to do this. And then how do you solve this equation? Anytime you have a rational number equal to 0, you set the numerator equal to 0 and solve. Okay, now how do you solve this equation? We haven't seen this semester. This comes up like I teach a college algebra class for actually a different institution, and I just did this problem. It's one of those weird quadratic-like problems. It's not quadratic because it's fourth degree, but it follows that pattern of quadratic, right? That is, like in a quadratic, it's x to the second, x to the second, x to the first, x to the 0. This one has that same ratio, right? If it's 4 to 2 to 0, 2 to 1 to 0. I know if you haven't seen this in a while, I wouldn't do this to you on a test, I don't think. But my point is, if it factors like this. Right? It's like factoring 3x squared plus x minus 4. And then it'd be 3x times x to get 3x squared. But if it factors, it could factor like this. To get 3x to the fourth, it's 3x squared times x squared. That's 3x to the fourth. And then I could figure out how to get 4 and 1. And it's, I mean, it works the same way. The next step will be to set this thing to 0, which will be quadratic itself instead of linear, and to set this to 0. So I think I can get there by doing this and this. And tell me if that's right. 4x squared. Nope, that's not right. Try that again. I need to get a 1 as my coefficient. Right, so 3x. Wait a minute. That's what I wanted to do. That's 4x squared minus 3x squared, right? Tell me if you like that guy. Plus 4x squared minus 3x squared is 1x squared. I think that's right. So if you FOIL that out, you get the fourth degree. And I know you haven't seen that probably in a long time, if you've ever seen it. But it does factor like that. And then from there, you go, you set this to 0, which remember, this guy comes up a lot. There's no solutions to that. I don't want you guys wasting time on these guys. Anytime you have an x squared term plus a number, it's always positive, which means it can't be 0. And when I say always positive, I don't mean non-negative. I mean, right, non-negative includes 0. Always positive is always greater than 0. So it cannot be 0, right, unless the 3 were negative. So that has no solutions. And, of course, this guy has 2 solutions at x equals plus or minus 1. Okay, Lindy, does that make sense? That's just a tough algebra problem. That's a good one, though, to see these weird things every once in a while. Yeah, if you ever have, like, that would also work, I think, if you had, like, 3x to the 8th plus x to the 4th minus 4, right? You could factor that, and then this would be a 4, and this would be a 4, but it'd still work. And then you could go from there. Okay, good. Lindy, did you have anything else from the review?
No, that's everything. Thank you.
Anybody else? Okay. Let's see. What can we do? So here's my list. Let's go back to my list. We just did a couple of these ones, right? At least first derivative. Oh, I guess the question for this one then was to find the intervals, right? And max min. I can do that if you guys want to see it. It would just be, I think I answered like the hard part, the algebra part for this one anyway. But the rest of the work, of course, would be to do the test. We can do this. I don't think we need to. But yeah. All right, this is your first derivative test. Oh, by the way, I graded your quizzes, and not many of you did the second derivative test to prove that cost was it was a minimum, what you're supposed to do. And I let it slide, but just be careful. You are answering the question in that you found the minimum cost, if you remember your quiz. But during that process, you should be thinking, you should be validating that, in fact, it is a minimum, right? And that's what you do that with this. The easy way to do it is the second derivative test. So make sure you do that on your test. Like, it's not part of the question, right? That's up to you to figure out, all right, I'm doing optimization. Do I really have a critical number that gives me a max or a min? Second derivative test is the best way to do that. Okay. Let's go back to the test review. What will you have to do on Thursday? All this stuff. Okay. Yeah, I don't know. What do you guys want to do? Remember your absolute max and min. Don't forget you have to test those endpoints. We should probably do one of those just to remind you about those. And then we could always use work on the word problems. Let's start there. I got, they're in here somewhere. This is a related rates problem. This is a optimization problem. Oh, this is your quiz problem, so we could go through that if you want. Oh, I don't know. Does anybody want to see the quiz? You all seem to do pretty well on it. Let's do it. It won't take long, I don't think. Okay, so here's your optimization problem. A rectangular aquarium needs to be built with a volume of 10 square meters. All right, let's see. Jonah, can you give me one equation, or how about the volume equation? So you got this guy. And Jonah, use my letters.
Okay.
What do you think about the volume?
Volume equals 2x times x times y.
Very good. 2x squared times y, and that's 10, right?
Yep.
So anytime you're given a value, that's typically your secondary equation. Jonah, you want to try the the equation? How about surface area? This is how I look at this one. Can you give me a surface area for this one?
Yeah. So the surface area equals 2x times y times 2.
Okay.
So in parentheses, 2x times y.
Very good. That's two of these guys. 2x times y. What? Keep going.
Plus 2 times x times y.
Right. So two of these guys, right? Very good. 2 plus 2 times x times y. And are we missing anything?
And then the base. So 2 and plus 2x times x.
Right. So plus this guy, right? The base of this thing is 2x times x, or 2x squared. Very good. Lindy, the terms primary, secondary don't matter. They don't matter. Is that right, grammar? Yes. Yeah, they don't matter. I don't care what you call them, as long as you can solve the problem. That's all I'm really interested in, and you're showing all your work. So I tackled this like this way, I think, is how I thought of this, because we've done these. That's a 4, that's a 6. And now I bring in the cost, right? Because it was $6 for one side. Here it is. $10 for each of the 4 sides. Wait, base is $10. Okay, so now we're just going to multiply this by 10, right? And we're going to multiply this by 6. And we don't really need our units there. So your cost equation, right? So I knew the cost was going to be just multiple of the surface area. So the cost equation would be 36xy plus 20x squared. Yes. And then here's the issue, like usual with these. I got a function I want to do calculus on. That's what I need to optimize, right? Take derivatives, set to 0, and so on. However, it's a function of 2 variables, right? And that's why we come back to our secondary equation. If you solve this for y, divide both sides by 2x squared, 10 over 2x squared, or 5 over x squared, right? If I solve that for y. And now I can write my cost as a function of x, and it's 36xy plus 20x squared. That guy goes away. One of those goes away. 150 plus 30. At least one of you just had, it looked like you did everything right, but you had that number wrong. I think that should be 180, right? Yeah, that looks right.
I got a question.
Yeah, go ahead.
For the surface area equation, the 2x squared, shouldn't that be multiplied by 2? Well,
Oh, good question. Now, Joseph, I see what you did. I'm going to look at your quiz again. There's no lid for this thing, and that wasn't. I guess it's kind of assumed that aquariums don't have lids, but I don't know if that's a safe assumption. So I'm going to relook. I'm going to look at yours again. I was wondering what you were doing. Yeah, I think maybe that's something I should probably tell you, because does an aquarium have a lid? I would say no, but aquariums can have lids, right? So yeah, I would consider that correct if you told me that this thing has a top, right? But it also doesn't give you any information about the top, right? It gives you information about the base and the sides. So it's not really, so I can see how that's confusing, but it's meant to be, Joseph, that there's no top. But I could see how you would think there might be a top. Okay. And I guess I could be more clear with that, but I'll look at yours again and see if it's right, assuming that this was, so what did you have? You must have had this would be double, right?
Yeah, I think that is what I had. Yeah.
Maybe that's why. Yeah, that would be a 40. But I'll look at it. I'll look at it and give you some points back if you did everything else right.
Sweet.
Good question. Yeah, good question. Okay, and now from here we do the derivative. That's x to the negative 1, negative 180, x to the negative 2 plus 40x. And then I'm going to set this to 0. And I know I'm going quickly, so just ask me questions if you have them. I like to write that like that because I know how I'm going to solve this. I'm going to add it over. You can do this however you prefer. There's a couple ways to do the algebra, of course. But ultimately, I got 180 over x squared equals 40x. And I'll just multiply both sides by x squared, which gives me 180 equal to 40x cubed, right? And then I divide by 40. And then I get, what is that, 9 halves, right? 9 halves equals x cubed. So the x that gives me the critical number now, it doesn't necessarily give me a minimum cost. I'm pretty sure it gives me a minimum cost. But if I really want to be sure, and this is something I expect you to do, is to do the second derivative test. Or you can do the first derivative test if you want. I think the second derivative test is easier. Here's my first derivative. So my second derivative is, that's x to the negative 2. So that's 360 x to the negative 3 plus 40. And it's pretty clear if I plug in a positive number to this guy. And you can give me a decimal for this if you want. That's fine. You got your scientific calculator. It's pretty clear, I think, that that's going to be positive, right? Any positive number you plug into that function will remain positive, which means we are concave up, which means it is indeed a minimum. Okay, and I'll skip the last step is actually to find the cost, which means you take this and you plug it into, where'd it go? This, right? There's my simplified cost equation as a single variable, as a function of a single variable. It was something like 163 or something like that. Okay, do you want to try one of those? We could do this one, or we could do, I don't know, these take a while. What do you think? Jake, what do you want to do? Do you want to do a optimization? Do you want to do a related rates, or do you want to do something else other?
Optimization.
Good. Stay with it. All right, guys, I'll give you a few minutes. I don't want to give you I'd like to give you time, but I want to make sure we get to everything. So see how far you can do with this, and then I'll probably start before you finish, but see what you can do with it. This one is probably towards, especially if I don't give you the picture, it's a little challenging. So let me give you the picture here. Trough water is 8 meters. Okay, so it's a trough whose base or front and back is an isosceles triangle, right? So that's an isosceles triangle, and then it's like it's three-dimensional, right? So it looks something like this. No, that's a bad picture. And that's not too much better, but you get the idea. Let's see. Well, this is the outside exterior wall, I guess. Okay, so it's a trough, and it's getting, let's see, a trough of water is 8 meters in length, and its ends are the shape of isosceles triangle whose width is 5 meters and height is 2 meters. If water is being pumped in at a constant rate of 6 cubic meters per second, what rate is the height of the water changing when the water has a height of 120 centimeters? Okay. So these are tough. When you look at these, it's like, what is this thing asking, right? It's confusing. There's a lot coming at you. So you just got to kind of break it down piece by piece. I hope the volume formula shouldn't be too bad. There's probably somewhere a geometric formula for volume of this thing, right? It's a pyramid, right, is what it is. However, the volume formulas aren't too hard to derive, right? It's just the area of an end times its length. Does that make sense? So the area of this thing, that's 2 dimensions, right, times the length of it, and that'll give you your volume. That's it. That's all volume is. So that's one of them. So right, the area, remember, area, so you need the area of a triangle, 1/2 base times the height. Trough of water is 8 meters in length, so this guy is 8. Width is 5. Call that 5. And the height is 2. So the height here would be 2. So we've done these kinds before, right? In that you got to picture water in that thing, right? And then there's going to be a similar triangle that you can work with. I think you're going to do the calculus after you do some substitution. Okay, so what am I missing from my volume equation? My volume equation is not complete, right? It's just the area. I just have the area of a triangle. Does it make sense if you take the area, the 2 dimensions, just multiply it by this distance that you got the volume, right? So remember, if you put some water in here, oh, this isn't going to go well probably. If you put some water in here, what's a variable and what's not? Something to always think about. What's constant? Does it make sense that 8 is constant? Right? I almost gave this guy a name, let's call it W, and wrote my volume formula like this, right? The area of the triangle times the width, right? But I don't need to do that. The only variables here are your height of the water and the width of the water. Okay, in this example, the height, and maybe let's call this base, the base of this triangle, right? That is your water as it's filling up. Okay, so does it make sense that W is not W, W is 8? Okay, remember that's my step 1, by the way. Step 1 is find an equation that represents the volume of what's changing, and that's the water. Right, so we focus on the water. So the volume is 4 times the base times the height. Okay, and remember, we've seen a couple of these where we were able to like sub out one of those. So that's the question, I think. Do we need to sub out a B or an H? If you can, do it, because it's going to be way easier if you do that. But let's see if we can tackle this from, is it necessary to do it? Do we want this as one variable, right? We don't have to oh shoot, Jake, you said optimization, right? This is related rates. I'm sorry, we'll do optimization next. This is related rates problem. The reason I just thought of optimization, because optimization, we always need to have my function that I'm going to do the calculus on as a single variable, right? But these we don't, because we're given some information about they're all functions of time. It's a lot different than those optimization problems. Optimization problems are like regular functions of x. Okay, so this one we've worked with these before. Remember, if I take the derivative of my equation 1, I'm going to have 3 derivatives: the rate at which the volume changes, the rate at which the height's changing, and the rate at which the base is changing. I'm calling this base. The 5 is the base. All right, and then this guy right here is the base at any moment in time. This guy. So yeah, we've done them as multiple variables and we've done them as single variables. That is, I can write, if I want to write volume as a function of a single variable, sometimes I do it, sometimes I don't. So do you recognize that now? Well, let's just continue the process and see. I mean, you might recognize it, right? You got dv dt. What else we got? At what rate is the, okay, we want dh dt, and that's it. Okay. So you might realize now that we don't have enough information to answer the question. I cannot find dh dt if I only have dv dt, and I don't have dv dt. Right? So we got a problem. You might recognize it now. And if not, you could keep going. You could say, well, what's my step 2? I want to find, oh no, step 2 is given rate, sorry. Given rate in calculus terms would be dv dt in this case, which is 6. Step 3 is find dh dt, and then we say when what? H equals, and we got another problem here. Minor problem. Centimeters. Right, we got, go ahead, Lindy.
Aren't we finding dB dt?
At what rate is the height? Well, it depends on what you call what, right? It says, at what rate is the height of the water changing? So for me, I'm calling this distance H. Does that make sense?
Okay, yeah, I was actually.
And then
looking
I'm
at the
calling
wrong
this thing,
bit.
I'm calling this thing the base. It's like, for me, it's an upside down triangle. The base is horizontal, the height is vertical. Does that make sense? But you could, it doesn't really matter. If you called the other guy B, then you'd be fine.
Yeah, I was looking at the second question, I think is why I was confused.
Okay, yeah. Sorry. There's 2 questions here. Right. I'm just working on the first. I didn't even really look at this one yet. I'm just working on the first. Oh, I know why you're confused, because I'm looking at the 120. At what rate is the height of the water changing when the water has height? Oh, there's another 170 or 120. Yeah, same moment in time. Same moment in time when the height's a particular value. Okay, so the issue is one of our values is in meters cubed, the other one's in centimeters, right? So that's no good. I think we could change meters cubed to centimeters cubed if we want, but it would probably be a lot easier to change centimeters to meters, right? So these things get thrown in there to kind of just throw you off or something to think about. But that's not too bad of a conversion, right? Everybody knows that 120 centimeters, there's 100 meters, or 100 centimeters rather, in 1 meter. So in other words, you divide by 100, right? 1.2 meters. Okay, now here's the issue. This is where I want to stop. We've done, like I said, I think the cone problem was like this one. If I take the derivative of this thing, I'm going to have to use the product rule. I'm going to have a dB dt and a dH dt, and that's no good, right? I'm trying to recognize now that I'm not going to be able to answer the question that way, right? Because I only have dV dt. I'm trying to find dH dt. When I take the derivative, there will be a dB dt in there, and then I'm going to have 2 unknowns. I'm not going to be able to solve it. Okay, so we're going to have to go back to our similar triangle thing to get this. And sorry, let me try and label this. This guy right here is H, and for me, and this guy right here is B. Okay, so remember the similar triangle. So you have that little triangle, whom I've labeled the base B and the height H, and I have the bigger triangle whose base is fixed at 5 and whose height is fixed. It got kind of scribbled over there. It's fixed at 2. Okay, so W or B to 5, B, right? Similar parts of similar triangles are equal, or the ratio of similar parts to similar triangles are equal. So B to 5 has to be the same as 2 to H. H to 2. Sorry, H to 2. Got to put them in the same place. B to 5, B to 5, H to 2. Okay, and I think that's really the hard part. Once you write V as a, and you might not have to do that, right? Sometimes you're given enough information about the other variables or the velocity of the other variables, right? In this case, you're not, but you do have to decide which one of these to solve for. Oh, what do you think? Megan, are you still with us? What do you think, Megan? Which one of these are you going to solve for? Do you want B equals or do you want H equals when you do your substitution?
Probably H equals.
So if you do, well, let me ask you this. Which one of these in this equation here, which one do you want to sub out? Which one do you want to get rid of?
B. Do you want to get rid of B?
You want to get rid of B, right? Because we need to find dH/dt. So if you want to get rid of B, then you should solve this for B. Does that make sense? My question was weird. You want B equals something, right? But you're right. You want to get that B out of there. So your volume function is just dependent on H. Good. So B equals 5 halves times H. And then we go from there. Sorry, I was going to let you do that on your own. I got a little carried away. Go ahead. See if you can give me an answer now. And then you can try the second question. You could try that one. It's not too bad, I don't think. It's a little different. But go ahead, take a couple minutes, see if you can finish this one off. What do you think, Gabby? Gabby, can you see how I got this 10/8 squared after the substitution? Does that make sense?
Yeah, it makes sense.
Did you get a value for dH dt?
Not yet.
Okay. What's going to go here? What's dV dt?
There'll be 6. then.
6, right? That was one of the given information. And what's H? For this particular moment. What do you think? What's the height? I think we had that somewhere.
Yeah. Then there'll be 1.2.
1.2, very good. Okay, so once I have that in there, I just got to go 6 divided by this product, 1 point, that's 24, I think, right? 20 times 1.2 should be 24. And then there I go, that's a fourth, right? Sure, that's right. 0.25, and then our units. So remember, that's H, so it's not square. Remember, it's meters because we converted meters. So it's not square meters per second. It's not cubic meters per second. It's just meters per second. Don't forget your units. Okay, so that's a typical related rates problem, but for this piece right here. But for this piece. So look out for those. Every once in a while we have to sub out one of our variables, right, by using some old geometry. What else was atypical? This was thrown in there. I usually don't do this to you, but you never know. Oh, this one. Centimeters versus meters, not the same unit, so we have to convert. That was an easy conversion, no big deal. How about this bonus question here? At what rate is the width of the water changing when the water has a height of 120 centimeters? Okay, so width, I should have probably used W instead of B, but B is W. B is the width or the base. I probably should get rid of that. Okay. So I think we could start all over and do this one again. Just do it the other way around, right? The first question was, at what rate is the height changing when the water has a height of 120? The next question is, at what rate is the width changing when the water has a height of 120 centimeters? So I think we could start all over. However, if we can just connect, I think there's an easier way to do this one. If we can just connect W and H, right, and kind of do a whole different problem that just relates W and H, or I'm sorry, B and H. If we can just find a function that just relates B and H, and then we take the derivative, then we have dB dt and dH dt, then I think it'd be a lot easier. I'm pretty sure we can start all over and just write this in terms of B. We'd have to use this formula, right, to sub out the H. And I think we could get there. I'd have to do some math because it's giving me the H and I would need a B, right? I would need the B for that, which I can do because I have a triangle. But it's a lot easier if I just use this as my first equation, right? If you think about what they're asking, they're just asking us for dB dt when H is 1.2. Right. And in fact, it's the relationship. It doesn't even matter what the height is because the rate should be going just based on that coefficient. Right. If you took the derivative of both of these, which is how we're going to approach this one, then I don't even need H. Okay, it doesn't matter what the height is because the relationship will be the same. It'll just depend on the 5/2 and the other two rates. In other words, I can do a whole new problem to answer that second question. And my step 1, I don't even care about the volume, right? There's nothing about volume in here. I got my equation already written. We already found dH dt. That says dB dt when H is 1.2, right? Which we don't even need, I don't think, but I'm just trying to follow my procedure. Sorry. Let me zoom in there. Here's my question 2, right? It's just asking me to find dB dt. Say, well, all right, I already got a relationship between B and H, and I know everything I need to know about H at this moment in time. So I can jump right to that one. Does that make sense? Who's got questions? Because this one we can finish up real easy. dB dt equals 5/2 dH dt, and dH dt we know is 0.25. So my answer then is, what is that? That's just 5/8 meters per second. Okay. No questions? Let's see, we've already been here an hour. I say we do the one more optimization and then we'll take a break. Okay, so I think it's good we're spending the time reviewing out like these word problems, because the other big portion of the test has to do with taking derivatives, right? Which you've already done a bunch of, right? The whole process we could review, but you've been doing derivatives a ton. And then the new part's the antiderivatives. Okay, so I think it's good that we review these more difficult word problems, even though the 2 word problems will make up, I'd say, just about 20% of your test, right? Because I'll probably only give you one of each. They seem like 10 pointers to me. But let's do this one. I'll give you some time. See if you can figure it out. So again, switched optimization. Not related rates, right? Not functions of time, functions of whatever, X and Y maybe in this case. Okay, so you have a choice, sorry. To interrupt. We have a choice. You can either call this distance X I don't think it matters. This distance x, the page distance, or the printed distance x. Right? I don't think it matters. So pick one if you want to. If you're not there yet, I'm gonna do it this way. I really don't think it matters, but I'm gonna do it this way. If you have questions, let me know. Chat them or ask them. I got my setup so far. Okay, so you can check to see if you agree with my, I guess, what I'm calling primary equation, the equation we're going to do the calculus on. So I got my primary right here, right? I'm going to maximize the area of the paper. So that's out here. Oh, sorry. Take that back. That's my secondary. I have 200 square inches to use, or that's what it needs to be. It's going to be 200 square meters, and I want to maximize the printed area, right? Which is represented in my case by x minus 2, y minus 3.5. All right, and then these ones work same way. Solve one of your equations so you can sub, and here's my new primary equation without a y in it. X minus 2 times 200 over x, which is what y equals, minus 3.5. FOIL, 200 minus 400 over x, minus 3.5x plus 7. I guess I could combine those, right? And then my area equation as a function of only x will be 207 minus 400x to the negative 1 minus 3.5x. Who's got questions? Adrian, did you make it that far? Did you get this?
I kind of did in a different way.
That's fine. Did you call this distance X or Y?
Yeah.
Okay,
I
you
kinda-
can do it. You can do
I
it that
use-
way.
Yeah, I kind of used the secondary way, the secondary equation. I don't think that was right.
Oh, you don't want to do calculus on this one because that's like a fixed value for the area.
Oh, okay.
I mean, there would be another way to set it up, which I thought is what you're saying. If you call this, like, let's call it W, then you'd have like an expression W plus 2, and you have expression Y plus 3.5, and you might get there that way. You might get there. But if you set it up my way, then this should be your area function, and then we'll differentiate this guy. Ella, did you get this area function?
Well, I forgot to simplify the A, so I just did the product rule instead.
You do
So
that.
I
Yeah, you
might
can
have
do that.
gotten it different. My
We'll see what you
derivative
get.
ended up being 400 over x squared minus 3.5.
That's right. That's what I got. So you did that by the product rule. And when I take the derivative of that, I get the derivative of this would be 400 x to the negative 2. And derivative of that is just 3.5. So yeah, you get the same thing. So you got 400 over x squared minus 3.5. Then we got to solve this guy. This doesn't look like it's going to work out very nicely, but that's okay. So x squared equals 400 divided by 3.5. And then the x that I think is going to yield a maximum will be whatever this is. That's about 10.7. That's what I get. Inches. Okay, and remember, I think that's going to yield a maximum, but I want to make sure. Oh, I got something mislabeled here. This is a prime. So a double prime would be negative 800 x to the negative 3. And of course, because of that negative value there, any positive I plug in will give me a negative value for my second derivative, right? So a double prime second derivative test is certainly going to be negative. Oops. Negative. Okay. Who's got questions? That's a pretty typical one. That would probably be easier if I gave you the picture. All right, if you mess up with the picture, then you're going to be in trouble. If I gave you this, then I think the area for the printed area is pretty straightforward. The primary, pretty straightforward, sub one into the other, and then go from there. Let's see if we answered the question. What dimensions will give the largest printed area? So no, we did not. But we could, right? We could go and solve y just by dividing 200 by our 10.7. Okay. No questions on that? Okay. So let's see. In a review, typically I say if you feel pretty good about it, I won't keep you for the rest of the class. So if you're feeling good about the test and you're going to review on your own, then you're free to go. Otherwise, we're going to take a break and I'm going to have you do this curve sketch problem. Okay. So let's take 5 and then I'll just leave it up here. When you come back, see how far you can get with that. Do the whole thing. As much as you can, first derivative, second derivative, graph that function. And I'll be back in 5 and then I'll start slowly doing it and see what you get. See if you can graph that 5th degree polynomial. Yeah, you guys can see how you do with this one. I'll just slowly walk through it and you guys can just work on it. Let me know if you have questions. Okay, check to see if you got your intervals right or if you made it that far. I got up, down, down, up. Okay, see if you got that with critical numbers -1, 0, and 1. Means I got one maximum, I got one minimum, and then I got that thing that where your function levels off and it keeps decreasing. Decreases, levels, decreases. So nothing going on at x equals 0. If you made it to your second derivative, you get what I call possible inflection points at, here's my second derivative, 30x times 2x squared minus 1. So you get possible inflection points when x equals 0 and at plus or minus a half, square root of a half rather. 2x squared minus 1 equals 0. Solve for x, you should get the square root of a half. By the way, that's our famous number from Trig. That's square root of 2 over 2. So you might know that as a decimal. I went to decimal down here because I didn't want to think too hard about it. That's 0.707, something like that. So I just said 0.7. I just made sure I was in the right interval by staying kind of far away from 0.7 since I'm rounding. And if you do that, you should get down, up, down, up. Okay, anyone have any questions or disagreements? It's like some of you guys are still working. I'll give you just another minute or two. Go ahead and keep doing what you're doing, then I'll graph it. See if you can bring all that together. I didn't label I got a couple inflection points here. 1, 2, 3, it looks like. And I got one max and one min. So I get a maximum at -1, 5, and a minimum when x equals 1. And the output there should be 1. these ones, you're kind of forced to use your calculator for your inflection points, right? Because when I plug negative square root of a half or negative 0.707 into this thing, well, there's no, and plus if I have to graph it, I'm going to have to go to my calculator. There's no choice there. You should get about 4.2 for the negative is what I got. Let me know if you get something different. And for the positive, I got like call it 1.8. Okay, so I got all the, by the way, I didn't ask you for the pre-calc stuff on this one because it's actually really complicated. Well, you got the y-intercept. That one's easy, 0, 3. I could ask you for that. The x-intercept I can't ask you for, though, I don't think. There could be 3, but remember, that is not an easy equation to solve. All right, this one's kind of hand-picked so that the derivatives are easy to solve. But that x-intercept is a pretty tough equation, right? We don't have methods for 5th-degree polynomials. So we don't know where it crosses the x-axis. That's okay. We got a lot of other information. I'm going to start plotting some points now. All of these, right? And then I'm going to see, and then I'm going to follow my increasing, decreasing, and then I should be done. Where'd that go? Oh, there it is. Come on. Okay, let's see. Try that again. All right. I have a max at negative 1.5. If we got the rest, now we should be good, I think. Negative 1.5. Oops, that's 6. Negative 1.5. I got a min at, where was that? 1.1, right? Oh, I don't like this graph. It's too bunched up. Let's call this negative 1, negative. Yeah, that'll be a little bit better. Negative 3, 1, 2, 3. Negative 1.5 was my max. 1 was my minimum, right? I think. Inflection points, 0, 3. The intercept was an inflection point. That's right here. And then I got to try and find those more difficult inflection points. Where were they? 1/2, negative 1/2, negative square root of a half, which is negative 0.7, 4.2, negative 0.7, 4.2. Now let's make them, I don't know, green for inflection point. Nope. That's the minimum. And then 0.7, 1.8. About right there. I probably could do better with a more stretched out graph. That is, the whole thing should be between negative 1 and 1 to get my those inflection points looking better. But I think this will be okay. In other words, I should have zoomed in. That's a max. That's a min. Okay, so it increases to the first pink dot, and it's concave down to the first green dot, right? And I'm not real sure where it crosses the x-axis, so that's okay. Increases, and it's decreasing. Actually, I should say decreases to the second green dot, but it flips concavity right here, right? So now I got to go to concave up, right? It should flip if the green dot's an inflection point at negative 0.7, whatever that was, 4.2. Then I got to switch concavity, but I got to keep decreasing. Okay, so can you see the concavity there? Sort of. And then it levels off, according to my first derivative. It levels off there, but it doesn't bottom out. It keeps decreasing, but we flip concavity again, right? So it's going to go to concave down. And I'm looking for this when I grade these things, right? Because you could just draw like a straight line through all those. And then you'd have a really rough graph, but you wouldn't have all the intricacies of the second derivative, what the second derivative tells you, and how it's flipping concavity, right? If you just draw a straight line, it would also follow what your first derivative is telling you. It would be decreasing over that entire interval. From -1 to 1, it decreases, right? Decreases, I should say. And then now we flip concavity again from here, from this point, the 0.7, what was that? 1.8, I think. It's concave up forever, right? So here is to the right of this line has to be concave up. And it's got to bottom out here. So something like that, pretty interesting looking function here because of those inflection points, right? So it should look something like that. This one is also an inflection point. This is a min. And this, of course, is a relative max and a relative min. Okay. How are we thinking about these? I got 5 minutes if you want. I was going to do I don't know. It'd be kind of hurried if we did a initial value problem. Or I can take a request. I got time for one more quick one. Want to see initial value, or does anyone have any requests? Kevin, we haven't talked to you today. Do you have any lingering problems you want to see? You feeling okay with initial value? I got time for one problem. Let me throw up an initial value problem right now, and then we'll call it a day. We got the most stuff. Oh, we better just do this one together. Okay. So I want you to solve the initial value problem, which means if this is your initial value problem, and then I got to give you, if I just said solve that differential equation, you find the antiderivative and then you have a plus C in there. If I say solve the initial value problem and I give you y of pi equals 1, and forgive me, I'm mixing up my y notation and my function notation, but I think that's okay. You'll see that every once in a while. That means when x is 1, or when x is pi, y is 1, right? Okay, let's see. Kevin, what do you think? What's your first step for these ones when you're trying to solve a differential equation? You know what to do first? This is the new stuff. This is from 4.1.
4.1.
What you did for homework? What were we doing in all those problems, basically? Instead of derivatives.
It will be cos of x changes into sin of x,
Very good.
and sin of x changes into negative
Very good.
cos of x.
And then we do the plus C, right? For the antiderivative, the general solution. And your two negatives become a positive. Very good. Gabby, you know what to do next? We got the antiderivative. We got a plus C. How are we going to use this information here?
Right now, I don't remember quite much, but I think we plug that one into yx.
Very good. You're right. You're plugging in the x value of pi and trying to find C. right? And remember, the y value here is 1. So what do you think, Joseph? What's c equal to?
I got C is equal to 2.
2?
Mhm.
What do you think, Lindy? What's c equal to?
Sine of pi would be 0. Cosine of pi would be -1. So
Agree or
0.
disagree? Sine of pi would be 0. Cosine of pi -1 plus c equals 1.
So 0. Or 2. Sorry.
2 sounds like we agree with 2. Does that make sense? Who's got questions? Oh, I knew I thought something was weird. I messed up. When I copied it down, I went from plus to minus. So I'm going to change the problem. I got a real quick fix for this one. The original problem, did everyone see what I did? When I recopied it, I put a negative here, and I think you guys just followed along with me. So the original problem was cosine minus sine, and that fixes everything. Cosine minus sine. Cosine minus sine. Kevin took the proper antiderivatives. Antiderivative of cosine is sine. Antiderivative of sine is negative cosine. So we get a plus there. Very good. And then we got some agreement on C being 2 after I rewrote my problem. And then we're done. So y of x equals, go back up to this line, right? Sine x plus cosine x plus c, which we decided was 2. Okay, good. That's it for today. My Wednesdays are just kind of all over the place. I got to change office hours again, so I don't know if anyone was coming. I know Gabby, you come sometimes. So it's gonna be tomorrow evening instead of tomorrow morning. So I'm gonna post that on the announcements. So if you guys want to do any last minute studying tomorrow night, I'm driving tomorrow, so tomorrow night I'll be available. I'm not sure what time yet, but probably like 9. So a little bit later, but I'll be there if you have last minute questions. And then regular office hours on Thursday if you have any questions, okay? Otherwise, study up, and I will see you all on Thursday. Go ahead, Lindy.
How do you know like when to write the answer to these? Like, in what way, if that makes sense?
The initial value problems.
Yeah.
So anytime you're asked to solve a differential equation, then if it's like, depending on what this is, whatever notation we're using, then your answer, if it's dy dx, your answer should be y equals. If I gave you like f prime, then your answer would be f equals, right? The antiderivative of how the derivative is given. Does that make sense? The solution to any differential equation is whatever derivative is in your equation. In this case, this is the derivative. Your solution is the antiderivative of that, whatever notation we're using. So if it's dy dx, your answer should be y, right? And I know I kind of mixed up my notations here. So y equals or y of x equals. If it's f prime, then your answer would be f, and so on. Does that answer your question? And if there's an initial condition, you shouldn't have a c in there. If there is no initial condition that says solve like for the general solution, then you'll be done at this point, the plus c. Good question. Any more questions before we go? Okay, you know what to study. No surprises. You know what's coming. Just be ready for it. Office hours, I'll post an announcement, be tomorrow night, Thursday 11:15, and then I'll see you guys at 3:10 on Thursday.
Thank you.
Yep. Bye-bye. See you guys.
Thank you.
See ya. Oh, Gabby, were you planning on coming to office hours tomorrow?